Okay, left-hand side page, we have vocabulary folded over so that we can see the terms, not the definition. It's taped at the top of the left-hand side. Underneath, now hang on just a second, underneath, you're going to lay that page that has the 3 questions on it, but we need the notebook underneath. So one little piece of tape at the top, one little piece of tape on the top on the opposite side so that we can flip that up and get to the notebook underneath. So it's a little sheet that has the 3 questions on it. One little piece of tape on the top, flip it over, one little piece of tape on the top on the opposite side. I don't know who is yelling at me because you just All right, next, this is a little, well, actually, next, we'll just do this first part first. Okay, on the right-hand side on the bottom, put the 2 Post-it notes. On the right-hand side at the bottom, put the 2 Post-it notes. Line them up as close to the bottom as you can, but you don't want them dangling off the page. Right-hand side at the bottom, 2, did you get 2? Each stack should have 2 in it, so make sure that you have 2.
I didn't pay that much.
So, right-hand side at the bottom, 2 Post-it notes, line them up as close to the bottom as possible, but you don't want them dangling off the page. All right, next, lay on top of the Post-it notes this little graphy sheet. Go straight across the top of them. Now, obviously, we need to see the stuff underneath, and we need to see this on top. So one little piece of tape on one side, one little piece of tape on the other side so that we can see what's underneath. All right, so you should have one more little item to tape in. And we need to leave a little bit of room at the top of the page, so we're going to tape it in just above where you put your Post-it notes. So we're leaving some room at the top of the page, so tape it in just above where you put your Post-it notes. No, you can lay it down. You can tape it down. All right, are we good? Okay, we are back on the side that says data, yes? Okay, if you would please, when I draw your names, read for us the definition of data. Please read the definition of data for us, Hunter.
Information gathered during the experiment.
Absolutely, and so notice they say the word information, not numbers. Usually when we think of data, we think of measurements, numbers, and that is an example of data, but it doesn't have to be. So we could use qualitative observations or quantitative observations. So if something changes a color, well, that's data that we would write down. One of the labs that we do for soil contamination, we're looking to see if the chlorine level reaches a certain, the chlorine present reaches a certain level, and then at that certain level it's toxic. And so we're looking at the color change. If it has a certain color change, that means it's bad. If it has a different color change, then that means that it's not bad. So that's data as well. But most of the time when we think of data, we are thinking about numbers, and that's the example that we have. So, oh wait, what I want you to do first is take one of your highlighters and highlight the term data. Then with that same color highlighter, we're going to go to the data table, surprise, surprise, but I don't want you to highlight everything because some of this is data, but some of this is going to be a different example. So all of this information that's collected here, all of that is data. That's not data, that's not data, that's not data. All of this stuff is data. So choose how you want to highlight it. You can box it in, you can, pardon? No, not numbers. This what I have right here, because these are numbers, but they are not data. It's part of the experiment. So the information that we would have picked up from the experiment, everything that I've outlined what constitutes data. So you can box it in, you can highlight it however you see fit. So good point. It's not just numbers, because these are numbers up here at the top, and they are not data. They are part of our experimental method. We're setting up the data table to collect the data. All right, next we're back on our vocab sheet. Read for us the definition of mean, please, Maggie.
The number obtained by adding the data for a characteristic and dividing this sum by the number of individuals.
That is a really sciencey definition, and I bet you can give me a one-word term that means what she just read. So we know mean as what? Pardon? I just didn't hear what you said. What'd you say? Oh, I thought you said something. Somebody else over here said something.
You can read it.
But what did you say, though? What did you say? We're all in this together.
What, like, do you mean, like, what does it mean, like scientifically?
Well, we'll talk about that in a minute, but what did you say? What does it make you think of? Oh! Okay, okay. Yeah, okay. All right. So, but that's a perfect example of a lot of times when we're looking at vocabulary and defining terms, that there are more than one meaning for it, and that's fine. But yes, in this situation, I am talking about in terms of data. So yeah, but that's fine. You can throw that out there and we can say something like, okay, so we've heard this in this context before, and that's fine. That's not true. But for what we're doing right here, right now, we do want the mathematical data kind of situation for it. And so yes, that one word, quote unquote, answer that we would use would be average. On your vocabulary sheet, shut the little door, and then right next to mean, write average. Because you're probably more familiar with that term than mean, median, or mode. I don't know, I'm just guessing. Then take another highlighter, highlight mean, and box in the word average with the same color so that you know that this is associated with that. Then go back to your data table and take your highlighter. This time I do want you to box it in. Don't color it in. Just outline the bottom.
In the same way as average?
Yes, in the same color as average. Yes. Box in the bottom. And then I want you to write, oh, not average. Yes. I want you to write mean. Okay, we are going to save a little time here, so I'm just going to say what the mean of each one of these is. Mine is probably not going to fit within that box because I don't have enough room. So this first one right here, and don't write anything down yet because I want to explain something. 5, 1, 0, 4, 7, 3. So for us, we want to be a little bit more accurate. We're taking a step up, being sophisticated researchers. So whenever we run a math formula, if there's a decimal, we want 2 numbers after the decimal. So let's say this was 0.735. So what would this number, how would this number be different? Okay, because we'd round that up. So if this is 0.732, how would this number be different? 0.73, it wouldn't be different. We would just leave it like that and not round it up. Make sense? Okay, you can go ahead and fill that one in, 5,104.73. And make sure you fit it in your box. You can write smaller than I can, I hope. Okay. Next one. 5,056.07. 5,056.07. Fit it in that middle box. All right, last one. 4,988.50 gives us the 2 numbers after the decimal. 4988.50.
You said 50?
4988.50. All right, so we didn't have the time to go through and model it, so we're going to give ourselves some information just in case there is a test question that asks you about mean. So circle that last column, and here off to the side, we're going to add information. That way, if during a test we're questioning how we find mean, we have a nice example that will show us what we need to do. To find mean, add up all the data, then divide by how many data points you have. To find the mean, add up all the data, then divide by how many data points you have. Find mean, add up all the data, and divide by how many data points you have. And then it gives you the example. That's a comma, 64,851. There are 13 data points, so it's 64,851 divided by 13 gives us the 4,988.50. Flipping back to our vocabulary. Distribution. Read for us the definition of distribution, please. Kate. Yay!
Relative arrangement of the numbers of a
Statistical.
Populate, I can't say it.
Statistical? Like statistics? Yeah, statistical. All right. So. Oh, okay. Sorry. So yes, get you a third color highlighter, highlight distribution. Then the same color that you highlighted distribution. Now be careful, we don't want to get it all over the page because this graph information right here represents distribution. So I just boxed in the graph information in the same color that I highlighted distribution. So this would represent a graph from data that's collected out in the environment. It's showing you where the little blue line is coming from. So we graph the data and then they're using a little line to show the overall trend. The normal curve, standard curve, that's what we expect. That's what typically occurs when there are no selection pressures or anything like that. So grades, we expect most everybody like to be in the C range, and then you have a few D's and then even fewer F's. Most of them are C's. You have a few B's and even fewer A's. Typically that's what we expect, except when you're in the environmental science, we expect those grades to be skewed, which we'll talk about here in just a minute. But in a population of caterpillars out in the environment, if we're talking about the length of those caterpillars, there's going to be most of them that are middle sized. Then there's going to be fewer that are shorter, and then very few that are very short. Most are going to be middle sized. A few of them are going to be longer, and there's going to be very few in that environment that are very long. That's a normal curve. That's what we expect. That's what usually happens in nature. However, once again, if there's pressures on it, things get skewed. So we have a positive skew and a negative skew. So the positive negative part doesn't make necessarily a lot of sense. You just need to know, and I will tell you that it's positive because of where the tail is at. It's negative because where the tail is at. But that's just an FYI kind of thing. So you have a resource here that you can compare it to see if you have a graph that's skewed one way or another. You can compare it to your resource to decide whether that's a positive skew or a negative skew. There will never be a test question as to how is a graph skewed in terms of defining that term. Yes.
So like the way that I just was able to remember it is positive is left, negative is right.
Sure.
So
However,
negative, the opposite of negative would be right.
However, the only problem gets into when we're looking at the data. So that's great, but let me show you where it gets confusing.
Okay.
So underneath, we have these two Post-it notes. On the Post-it note, on the left, I want you to sketch a little graph. Make sure you label it. Length of tail is on the x-axis, number of lizards is on the y-axis. And then draw a line that shows that it has a positive skew to it. Go ahead and sketch that on the Post-it note on the left. Centimeters. So if we're talking about measurements, like length of the tail, are we measuring it in millimeters, centimeters, miles? It's going to make a difference. Y-axis, number of lizards. And then just some basic numbering just so we can get an idea of the pattern. Okay, so in the environment, lizard gets in a fight with a predator. Predator grabs a hold of its tail. Is the lizard done for? Is it dead?
No.
Why not?
Who does that?
Okay, you're one step ahead of me. So there's a lizard. That's, predators got it by the tail.
Yes.
And then,
It grows up.
okay, see how you're one step ahead of me? The grow back part, we have to lose the tail first and then it grows back. But that's the thing. So it loses its tail and it gets away and it survives. But once it loses its tail, it's got like a little stubby thing there until it grows back. So we're looking at an environment here. In this environment, do the majority of lizards have a longer tail or a shorter tail? It's skewed, positive skew toward the left. We have more lizards that have a shorter tail than have a longer tail. Do you see how I can say that? Okay. Okay, well, hang on. All I need is one no. They just want to hear my melodious voice. So right here, this tells me I've got 20, I've got 40, let's say that's 2.5 centimeters. So I've got 40 that are 2.5 centimeters, I have 20 that are 2 centimeters, I have another 20 that's at 4 centimeters. Then over here, I only have about 10 of each of those. My shorter lengths have more lizards than my longer lengths. So when I look at this trend in whole, I can say in this environment, more lizards have shorter tails than have longer tails. Did that help at all? Yes? No? A little bit. Okay, let me do the other one and that might help when we see the opposite to this. But the data, instead of being the normal curve, and don't put this on yours, I just want to show. So this would be the normal curve where in the environment, average is the most and then it drops off either way. That's the normal curve. This is not a normal curve. This one has a positive skew because the data is pushed because there's a selection pressure. We have lots of predators that are grabbing these lizards and they're trying to get away, so boop, they leave their tail so that they can survive. So there is a selection pressure. All right, next. On the post-it on the right, sketch this graph. Length of tail in centimeters on the x-axis, number of lizards on the y-axis. In this environment, general trend of tail length on the lizards. Do more lizards have a longer tail or a shorter tail? The graph is skewed so that we've got more lizards that are over here at the higher tail length. So in this environment, there's probably fewer predators, or they're not as good predators, or there's predators in there but not predators of lizards. So they're not losing their tail, or maybe they're faster lizards and the predators can't get a hold of them, whatever. But in this environment, the data is a negative skew, but that's where the right, left, positive, negative, all that stuff is confusing because it really doesn't always add up with what we're talking about, the trend. So if you've got a trick for it, that's fine, but you don't need it. Because if you have your spiral notebook with you, you can use that on the test.
Okay.
We're just wanting to match it up with the pictures of the general trend, of the general skew, positive or negative. However, on a test, you would have to tell me on that graph, not just if it's positive or negative skew, but generally speaking, what's going on here. These lizards generally have a shorter tail. These lizards generally have a longer tail. Did that help at all, Casey? All right. So now what I want you to do is I want you to take those two Post-its and go ahead and fold them up. And under the one on the left, we're going to write positive skew, and then we're going to explain the trend of that graph. There's lots of cats, hawks, predators in this environment, so the tail is lost often in that struggle to survive. Lots of cats, hawks, predators in the environment, so the tail is lost often in that struggle to survive. And that's why the overall trend in that environment is lizards with shorter tails. Megan, they meet you in the office, and this video link will be on Canvas, so you can do the rest of what you're going to go.
Thank you.
So if there aren't a lot of predators and you're not a lizard who's constantly fighting and battling to survive, you have leisurely time to let your tail grow longer. So if we have fewer predators in the environment, it gives those lizards time for the tail to grow longer, and that's what this graph was showing. So this was an example of our negative skew. Fewer predators in the environment, so tail can grow longer. Yes. Yeah. All right, so next, we're back over on the left-hand side. We're on this little page right here. Go ahead and flip that up because we're going to put some information underneath. So we're on the left-hand side underneath this little sheet. So this is going to be information about probability. Here is the formula to find probability. The number of desired outcomes divided by the total number of possible outcomes times 100 equals probability. The number of desired outcomes over the number of possible outcomes times 100 equals probability. example. Let's say I flip a coin, and I want to know the probability that it's going to land on heads. You probably already know that it's 50-50. But I want to show how to do this because you're not always going to have nice, easy numbers. So the number of desired outcomes is 1 because I want it to land on heads. The number of possible outcomes is 2 because there are 2 possible outcomes. It can land on heads or it can land on tails. Here's the part that gets people the most. To go from a fraction to a decimal, it is the top number divided by the bottom number. It is not the big number divided by the small number. Sometimes it is big number divided by the small number, but it's not always that. It is always, always, always the numerator divided by the denominator, the top number divided by the bottom number. You've got calculators in the little Ziploc bags, so don't need to worry about doing any of this stuff in your head. Use a calculator. So 1 divided by 2 is 0.5 times 100 gives us 50%. That's where the 50% comes from.
I just know that 1/2 equals 1/5.
And that's fine, so that, when you have a test question that's like 2 over 6, well, that's 1/3 instead of 1/2, so what is that percent going to be? But then you can say, okay, well, I know 1/2 is 50%, then you can kind of run through and do your calculator. Is it 2 divided by 1? Is it 1 divided by 2? And see which one makes sense because you know the answer. So in this example, I want to roll the dice, and I want an answer. I want a result that's either lands on a 1 or lands on a 2. Either one is good. So I have 2 desired outcomes because a 1 is a desired outcome and a 2 is a desired outcome. I have 2 desired outcomes. There are 6 sides on a dice, so there are 6 possible outcomes. It is not the big number divided by the small number. It is the numerator divided by the denominator. So 2 divided by 6 gives me 0.33, and in fact it gives me, I think, 0.33. We only need 2 numbers past the decimal. So just like with the mean, with the average, round up if it's 5 or greater, leave it as is if it's less than 5. Times 100 gives me 33%. Yep.
Can I, do that square with my possibility?
Say that one more time. Oh, like square that in? Box that in? Yes, absolutely. So you need a 4th different color highlighter. So yes, box all that in and highlight probability that same color. Yes, that same color, highlight probability, because that goes with this. Then go ahead and answer those 3 questions on the front. Write it out for yourself so that you can see the steps. If it's a test question, have you given yourself enough information so that you can come back to that example? Oh, we didn't read it yet, did we? We did not. How disappointing. Your fraction, your division, times 100, write the result.
think that you're rounding just a little bit too much. So when you run that through there, so it'll tell you. Oh, two numbers after the decimal, and then times 100. So I think you're running just a little bit too much. So on this one, whenever you do the division through the column do you have allergies? Only the penicillin. I'm not sure why it does. Okay, so we only have two numbers past the decimal. So what two numbers would you do instead of 0.6? Is the next by root. So then that will be there. And so now we can do division. Yes. And then two numbers after the decimal. And that's fine. You're working a little harder than that. You just need 2.6 and it's actually 6 or something. So there'll be a video link I'll put up there on Canvas, and then you get a chance to turn that around, because that will be everything that's in there for your podcast. We're going to move on to the next minute, so I don't have to go through all the notes that we can there, but it'll be helpful. Right, and that's what we just went through, and so we will do. But it's close enough, but yes. Is it close enough? Yeah. You can see how good. Exactly. Okay. When I draw your name, read for us the definition of probability, since we forgot about that. Definition of probability for us, please. Candace. All right, and so that's what you're finding out. When I flip a coin, there's a 50% chance that it's going to land on heads. When I roll the dice, there is a 33% chance it's going to land on a 1 or a 2. All right, next, sample. Read for us the definition of sample, please. Riley. Right. So out in nature, little critters, plants, animals, whatever, within an ecosystem, there are gobzillions of these guys. If you're trying to collect information about them and get information about a species, you're not going to try to get every single one. You're not going to measure every blade of grass. You're not going to catch every bird or every insect that's out there. You're going to get a sample of the population. So let's say I have a population of 40 pom-poms in a bag. I have a bag, I put the little fuzzy pom-poms in there, I got 40 different ones in there. I draw out 10. I'm not looking at every single one of them. The 10 that I draw represent the sample population. So I have a population of 40 pom-poms in a bag. I draw out 10. That 10 represents the sample population. Yes, on the outside of your vocab. Shut the door of your vocab, look on the outside of your vocab. Aye. The only one I remember now is
What's the word after I, sorry?
population of 40 pom-poms in a bag. I draw out 10. These 10 sample represents the population. This sample, I guess I could have grammared that a little bit differently. But those 10, if you keep reading it loud, represent sample population.
And that direction will get messed up.
Something like we. All right, fifth different color highlighter, highlight that, and we're good to go.